Welcome to ASHRAE's Tech Hour. Today's subject is indoor environmental quality, codes, impact on people, and considerations, with presentations on indoor air quality, thermal comfort, lighting, and acoustics. Presenting on IEQ is Dr. Marwa Zaatari, Vice Chair of ASHRAE Standard 62.1, Chair of the Risk Assessment Group for ASHRAE Standard 241, former Chair of the Environmental Health Committee, and ASHRAE Distinguished Lecturer. Thermal comfort will be presented by Robert Bean, an ASHRAE Fellow and Distinguished Lecturer, instructor for the ASHRAE Learning Institute, and member of ASHRAE SSBC 55. Our lighting segment will be presented by Deborah Steimel-Clair, a licensed professional engineer and certified lighting designer, currently serving as an associate professor with a background in lighting design, electrical systems, and code consulting. Our final speaker today, focusing on acoustics, will be Erik Miller-Klein, a licensed professional engineer and certified by the Institute of Noise Control Engineering, who is the former chair of ASHRAE Technical Committee 2.6 and active with ASHRAE SSBC 189.1. The learning objectives for this tech hour are: 1. Participants will be able to describe the health, well-being, and performance impacts of indoor environmental quality. 2. Participants will understand how the current state of codes and commissioning are creating market challenges and opportunities. 3. Participants will be able to explain how indoor air quality, thermal comfort, lighting, and acoustics affect building occupants. 4. Participants will be able to leverage knowledge and resources to optimize IEQ for future projects.
Hello, everyone. My name is Marwa Zaatari. Thank you so much for coming to ASHRAE Tech Hour. I serve as a Vice Chair of ASHRAE Standard 62.1 and Chair of the Risk Assessment Group of ASHRAE Standard 241. Much of my work focuses on performance-based indoor air quality, resilient design, and health-centered, energy-efficient building code and standards. I'm excited to talk to you today about a major shift taking place in our industry, the indoor air quality paradigm shift, and how new standards, new science, and new strategies are reshaping the way we think about our indoor environments. In today's session, I will explore two key areas. First, how indoor air quality affects our health, resilience, and sustainability. And second, the major updates that happen in ASHRAE Standard 62.1, the newly published ASHRAE Standard 241, and newly published Guideline 42 and 44. These updates truly reflect a new era in building science, one that recognizes just how critical indoor air quality is for human well-being, and also for building performance and our climate goals. Well, if we take a step back and look at the past 50 years, most of the environmental policies and scientific attention have been focused on outdoor air quality, so fixing our outdoor air. Well, the Clean Air Act is a clear example. It dramatically improved the outdoor air and remains one of the most successful environmental policies in the US history. Actually, the EPA estimates the benefit outweigh the cost of this act by a factor 30 to 1, which is amazing. Like, just think about how impactful targeted air quality regulation could be. But here's the challenge. Even with all this progress outdoors, most of our exposure to indoor pollutants actually happen indoors, in the places we live, we work, and we learn. For half a century, we just ignored indoor air quality. We didn't give it the same urgency, enforcement, or regulatory rigor. So to recognize this gap, actually there's a growing call to the EPA to extend its effort indoors to do a Clean Air Act, but for indoor air, and even creating national guidelines and standards. We truly need an indoor air quality revolution, one that mirrors at least what happened for outdoor air. Now, traditionally, our understanding for indoor air quality has been centered on safety and satisfaction. We focus on preventing immediate hazards and making people feel comfortable inside the space. But that perspective, as you can guess, is very narrow. Because one of the biggest things we've been missing is health. Yes, we do need health-based standards, and health defined in its broadest and most comprehensive sense. So, as you heard before, indoor air quality is not about preventing illness, it's about promoting long-term wellness, cognitive performance, and reducing chronic disease risk. The other one is productivity. And decades of research tell us that our schools and workplace, the air in those spaces directly impact how people think, concentrate, and perform. Research has showed us that poor indoor air quality results in measurable declines in cognitive function, academic outcomes, and increased absenteeism. And the third pillar is resiliency. And in this case, we're talking about indoor resiliency. So as we know, indoor air quality plays a critical role in protecting us against airborne diseases, wildfire, ozone events, and other outdoor air pollution, and the growing impact or threats of climate change. Now, the thing is that most of our current standards were never designed to have these threats in mind because we always thought that's like one-time event. So I present to you the new indoor air quality paradigm shift. We learned from the pandemic, wildfires, heat waves, and other events is that we need this indoor air quality paradigm shift in how we design and operate buildings. And these recent experiences really expose the shortcomings of our standards and guidelines. So this new IEQ paradigm shift is holistic. It blends health and wellness, all the resiliency aspects, and for sure, sustainability and decarbonization. So we want to make sure that our buildings have a human health-centric focus, but also they operate responsibly. So design operate responsibly in driving energy efficiency and carbon efficiency. So in this HVAC world we live in, the idea of indoor air resiliency is relatively new. Right, we typically talk about resiliency for outdoor air events. ASHRAE lead and other various proposed state and federal bills are now pushing this concept forward. So indoor air resiliency will expand the definition of preparedness. So it's not only pandemics, but could also be applied to endemics, to wildfire and extreme heat events. This shift is really transformative. It really moves us from reactive design to intentional, performance-based, and forward-thinking indoor air quality strategies. So to solve this problem, we'll start with the question, what is in the air? And it's important to recognize is a little bit of a complex, complex concept because we have complex mixtures of contaminants, or if you think about it differently, compounds in the air. Some pollutants come from outdoor air, like ozone, particulate matter, specifically in commercial buildings. Some come from indoor sources related to building materials, people-generated activities from people, from equipment, from cleaning agents. The point here is that indoor air quality is multidimensional, and our solution from design and operation, commissioning, maintenance must be designed accordingly to this idea of the multidimensional indoor air quality. Now, ASHRAE provides the backbone of indoor air quality standards and guidelines in buildings. So today I'm going to focus on ASHRAE Standard 62.1, which is the most prominent ventilation standard, applies to commercial and institutional buildings, not to be confused with 62.2, which is for dwelling, and ASHRAE Standard 170, which is for healthcare. The second is ASHRAE Standard 241, the new standard control of infectious aerosols, was published in 2023. And finally, ASHRAE Guideline 44, which provides strategy to deal with wildfire smoke. It was published in 2024. And I forgot one, which is Guideline 42, published in 2023, that provides beyond minimum strategies, beyond minimum of ASHRAE Standard 62.1. So these standards, if you apply them together, depending on the situation, will represent a major evolution in indoor air quality thinking. So let me start with ASHRAE Standard 62.1. It provides a definition of acceptable indoor air quality. And if you want a short summary, it's air where there's no contaminants at harmful concentrations and where the majority of the occupants find it satisfactory. That's pretty good, although the word acceptable sometimes gets criticism. But if you look at the definition, that's actually what we want. We want air that's safe, where most people in the space are satisfied with the air quality in the space. So to achieve this, the standard has two procedures to calculate mechanical ventilation rate. So how much outdoor air do you need? Ventilation rate procedure, widely used prescriptive approach, and the indoor air quality procedure, performance-based approach. Well, historically, ventilation was viewed as a primary method for improving indoor air quality. As you see in the graph here, if you want to get better indoor air quality, you increase your outdoor air. We've all heard the phrase, the solution to pollution is dilution. But relying on ventilation alone can be both energy intensive and carbon intensive, especially if you live in climates that have a big cooling load or a big heating load from the weather. Also, it raises the question, what happens when the outdoor air itself is polluted? In those situations, bringing outdoor air without any filtration air cleaning might actually worsen indoor conditions because PM 2.5 is one of the most important pollutants we have. So in contrast, the indoor air quality procedure is a performance-based procedure and would allow you to improve indoor air quality, but not only to depend on outdoor air. You can also take credit for gases and/or particulate air cleaning and also source control. So this makes it possible actually to apply the right amount of outdoor air, ventilation, filtration, source control, while at the same time getting better indoor air quality because you're focusing on specific contaminants, taking into account the outdoor air quality, and also could have the benefit of lowering energy use and reducing the carbon footprint. And just so you know, in ASHRAE Standard 62.1, we have a list of design compounds. So it's the first major list we have in an actual minimum standard adopted by building codes, a list of pollutants. There is volatile organic compounds, inorganics, and also PM 2.5. Now, what you need to know is that although there's a list, cognizant authority, and design limit, in practice, the pollutants that most often drive the calculations are only three pollutants: formaldehyde, which is a primary indoor source, and PM 2.5 and ozone, which typically outdoor sources if you talk about specifically commercial buildings. So then if you take these into consideration, the calculation becomes much more straightforward. Now, moving on to a topic that we hear a lot about is carbon dioxide. So the question for you here is that, is this a myth or fact? Carbon dioxide should be kept at 1,000 ppm in buildings, also recommended by ASHRAE. That's actually a myth. In reality, ASHRAE sets no CO2 limit for achieving acceptable indoor air quality. This number, 1,000 ppm, is a legacy misconception and was never a health threshold. Now, worldwide CO2 recommendation vary dramatically, but CO2 is best used as a proxy for ventilation effectiveness, not as a contaminant by itself that define indoor air quality. In short, to improve indoor air quality, we must move beyond the single metric like CO2. We can focus on actual contaminants of concern, the one that cause mostly or contribute the most to the burden of disease, filtration efficiency, ventilation quality, and clean air delivery to the buildings. Now, moving forward to ASHRAE Guideline 42. So ASHRAE Standard 62.1 committee was responsible to write and publish ASHRAE Guideline 42. It was published in 2023, and it provides best practices to go beyond minimum requirements. So it's not a standard, it's a guideline, but it lays out strategies for enhanced indoor air quality. For example, how to pick high efficiency filtration, how to validate air cleaning technology, a lot about continuous monitoring and proper commissioning. So the goal is that if you want high indoor air quality and you want to follow best practices, you can definitely go check the standard. Next, ASHRAE Guideline 44. Well, with wildfire becoming more frequent and severe, it's not a one-time off event. It's like more seasonal event that happen yearly. Guideline 44 offers essential guidance for protecting building occupants. So, for example, it includes recommendation for advanced filtration, building pressurization, refugees area, and operating procedures, what to do during smoke events. It applies to many different building types, commercial, institutional, healthcare, and multifamily buildings as well. Now, next, moving on to the last standard, ASHRAE Standard 241. It was published in July of 2023. It's a groundbreaking development. It was done at the request of the White House, and it established minimum requirement for controlling infectious aerosols. But it's also in new and existing buildings and applies to all building types, healthcare, residential, non-residential, or commercial. And it actually recognizes airborne transmission as a major pathway for disease spread. Now, ASHRAE Standard 241 is groundbreaking for many different number of ways. One of them is establishing an infection risk mitigation mode. Another one is equivalent clean air flow, which integrates ventilation, filtration, air cleaning into a single performance requirement. It has 25 space types, and the equivalent clean air flow ranges from 20 to 90 CFM per person. And that's not only outdoor air, it could be outdoor air, ventilation, and filtration. Also, it includes safety and performance for air cleaning technologies. Okay, so the end of my talk. To close here, the key messages from today is indoor air quality profoundly impact health, resiliency, productivity, and climate. Yet it remains really underregulated. Standard 62.1, most prominent ventilation standard. It has an indoor air quality procedure, performance-based, that allow you to achieve high indoor air quality and at the same time be cognizant of energy and carbon. ASHRAE Standard 241 introduced a new health protection layer based on a concept called equivalent clean air flow. Guideline 42 provide beyond minimum standard strategies and best practices, and guideline 44 provide us for best practices for smoke events. Thank you so much. I hope this will inspire a new and more proactive approach to indoor air quality. I'm going to hand it off to my amazing colleague, Robert Bean. He's going to talk to us about thermal comfort. Thank you.
Welcome to the segment on thermal comfort, where one of the principles are where the person goes, so goes the thermal experience. And just want to say thank you to Marwa for doing such a great job on the indoor air quality segment, obviously another important segment of indoor environmental quality. I do want to draw attention to the term indoor environmental quality. It is, in fact, the umbrella that represents all of the sensory systems that the human body has. And in this particular segment, we're going to be talking about the thermal comfort, or the body's ability to sense the thermal environment. One of the key principles about thermal comfort is it sits aside from what the requirements are of the building codes. The building codes in many places of the world have a strict requirement to maintain some defined air temperature, typically somewhere around 22 degrees C or 72 degrees Fahrenheit. But these requirements, although you can be in compliant with the codes, you may not be necessarily compliant with ASHRAE Standard 55. And we see that in many, many examples in buildings around the world, where you've got control devices locked behind protective cages with threatening notes, or people trying to trick the system to turning on or off by some other creative strategy. So we can get buildings that are designed again to codes, but have problems with the thermal environment. Oftentimes those problems are related to the enclosure or the architecture or the interior systems, or a mismatch in the mechanical systems. In other words, trying to solve convective problems with radiant solutions, or trying to solve radiant problems with convective solutions. So we can be in compliant with codes, but not necessarily the standards. And you'll see people do very creative solutions to try to bring spaces into their own realm of thermal comfort, even though the thermostat may be reading exactly what the building codes require. So the document that we use as practitioners to create spaces that people can sense and perceive to be thermally comfortable is ASHRAE Standard 55. And in 2026, it will be its 60th anniversary. It's one of the oldest documents that ASHRAE has in its stable of standards. And it is colloquially called the ASHRAE Thermal Comfort Standard, but its title is Thermal Environmental Conditions for Human Occupancy. And one of the key points about the standard is that it requires us to specify all of the factors and combinations of factors that address both the personal factors, the environmental factors, which are air temperature, radiant temperature, velocity, humidity. But we also have some other requirements, and we'll get into those later on. And one of the other points that is really important, that the standard is intended that we use all of the criteria. So there's many other elements in the standard besides sort of your personal factors, general factors, and local factors, and we'll discuss them as well. So the key principal definition of thermal comfort is, in fact, it is a condition of mind. Your physiology experiences the space and senses what's actually happening around it, and that sensation is then communicated to your brain through your physiological systems. And it is here where there's two responses. One of the responses actually happens at an above conscious level, where you actually express being cold or hot, and then you try to adapt. So these are above conscious responses. But there's also a below conscious response that gets into the more nuances of human physiology, the adjustment of blood flow based on pressure differentials controlled by your neurological systems. The act of sweating, for example, or shivering are also response systems. So it's a really elegant system, and as long as you stay healthy and maintain a good, healthy physiological systems, your thermal regulation will work fine 24/7, 365. It doesn't require any batteries, it doesn't require any program, and you don't have to read a 30-page manual number 6 font. Your body will do its thing to try to maintain homeostasis, which is its survival mechanism to maintain balance. But it also enjoys being out of balance, in a word that we call allostesia. One of the things that we do like to draw attention to is how the human body responds to the thermal environment. And this oftentimes can create conflict in discussions. But we know through the ASHRAE handbooks, the medical textbooks, the indoor environmental guidebooks, that the human body, the relationship that it has with the indoor environment from a sensible point of view, is predominantly radiant. Convection plays a role, respiration, evaporation plays a role in conduction, but of the sensible load, approximately 60% of that exchange that the body has is radiation, or 40% of the total exchange. So the things that we look at specifically in the standard is we want to know what people are wearing and what they're doing. And this is incredibly important because these are personal choices that people make. Some of the conflict that occurs in spaces is the restrictions that, for example, some corporations place on their staff in terms of clothing choices. But we know that when given the opportunity to adapt to those spaces, that people will generally have a much higher probability of feeling comfortable, as opposed to being forced to wear some clothing that just is not suitable for the environment that they're trying to maintain. One of the other important elements is what we call the mean radiant temperature, and I like to refer to the mean radiant temperature as sort of the geometric thermal relationship that people have. For example, the individual next to the glass, if this was a cold climate and that glass, even high performance glass, would be incredibly cold relative to his body. So his thermal relationship with that glass surface is going to be completely different than the lady on the corner of the building, where her relationship with the two interior surfaces is going to be much different. So the proximity that people have to dominant surface temperatures is going to have a much more stronger impact on their experience. So this mean radiant temperature is incredibly important. We also want to acknowledge the role that air temperature plays, but the air temperature that we're referring to in the standard actually is the air temperature around the occupant, not what is read on the thermostat. And collectively, the two elements, air temperature and mean radiant temperature, when we marry these together, we achieve what's called the operative temperature. We also want to look at the air velocity, that is the speed of the air flowing across the occupant. It's not the air coming out of the diffuser or in the duct itself, but in fact the airspeed across the body. We also do an assessment of these spaces using a representative occupant. That is, what is this person doing? What are they wearing? Where are they located in the space? And how does the mean radiant temperature and the air velocity and the humidity affect the person where they are doing what they're doing? And in spaces like, for example, restaurants, where you would have multiple representative occupants, we would do an assessment for each of those persons. So, for example, the clients coming into the restaurant and sitting down and eating will not have the same metabolic rate as the serving staff or the kitchen staff. So it would be wrong to assume that we only have one representative occupant in these examples. So we would do an assessment for each of the representative occupants. Humidity is also important, and we want to make sure that when we talk about humidity, again, we're talking about the humidity around the occupant. And we also want to discuss how vapor pressure differentials affect the person's ability to discharge heat via the latent processes. So if the moisture in the space is higher, the vapor pressure differential is higher than what is on the skin. In these extreme climates where we have high humidity and high temperature, low air velocities, then these moisture levels become incredibly important. We want the body to encourage it to shed its heat via latent processes. But if the vapor pressure in the space is higher than what's on the skin, the body won't be able to cool via the latent processes. So controlling moisture is very important in some of these examples. When people are wearing light clothing and doing low metabolic activities, we also want to look at some of the local factors. These are things like stratification, which is the temperature difference between the ankles and the head, and radiant asymmetry, which are the surface temperature differentials on either side of the occupant, both in a horizontal and a vertical orientation. We also want to assess the floor temperatures, making sure that we're not too cold or too hot. And we also want to pay attention to draft, both in the general format and also the ankle format. One of the key areas of interest for ASHRAE Standard 55, our technical committee SSPC 55, has to do with elevated airspeeds. We know that when we can elevate the airspeed with, for example, ceiling fans, we can achieve an equivalent cooling effect through this fan. We're not actually cooling the space, but the occupant's perception of the space is cooler. And it's much more energy efficient to use the ceiling fan solution as opposed to adding more mechanical cooling. So we would encourage those that are looking for compliance with ASHRAE Standard 55 that rather than defaulting to mechanical solutions for cooling, try to incorporate elevated airspeeds in your assessments. So we look at the personal factors and we look at the general factors and we look at the local factors. And as we're using all of these metrics, we want to assess the architecture, the enclosure, the interior systems, as well as the mechanical systems. So the key points here is that we want to use the representative occupant, understand that they have to be in the space more than 15 minutes for an assessment. We have to understand that when people are at a MET rate less than 1.3 and a clothing value of 0.7, we have to look at the local factors. The standard provides two methods of assessment: the analytical method, which goes through all of these details that we just discussed, and then also the adaptive method, which basically says that if your climate zone allows you to have a free run building where you can actually engage with the outdoor environment through the opening of windows and doors, that as long as the temperature profile achieves the objectives of the standard, then you can use the adaptive method. We also look at a number of other metrics in the standard that when you get into it, either taking one of the courses that we offer online or in person at the conferences, the ALI courses, we'll get into more of these other details and find more detail. So when I look at ASHRAE Standard 55, I really do see it as the quintessential roadmap for integrated design. It allows us to have an open dialogue with the architect and the client and all of the other design professionals, starting with solutions to solve thermal discomfort, first with the architectural design. This is by far the most important element that we look at, and then looking at the enclosure design, and then moving on to the interior design, and then the mechanical designs. Again, if we have radiant problems, we solve them with radiant solutions. If we have convective problems, we solve them with convective solutions. But together, these four elements, when we get everything working well together, we reduce the probability of people being uncomfortable. And that is the ethos of the PPD and the PMV approach, which is the predicted mean vote. And we know that when we get everything right through having open dialogues, negotiations on the different principles of architecture, enclosure, interior systems, and mechanicals, that when we get everything right, we have an incredibly low probability that people will be uncomfortable, which is the objective of the standard. There are some online tools available that are provided through the partnerships that ASHRAE have with different service providers, in this case with the Center for the Built Environment. It's a tool that allows the practitioner to input the values that they've calculated, and the tool then will crunch the numbers for you, and it'll tell you whether you're going to be in compliant with the standard or not. It's one of my favorite tools. It's wonderful to use in a design charrette, where you can show the client and the architect that based on their decisions for the architecture and the enclosure and the interior systems, that they're going to have a problem or not have a problem with the environment. So through that open dialogue process, we can tweak the different values by tweaking the architecture, enclosure, and the interior systems, and then if necessary, tweak the mechanical systems so we can bring all of this into compliance with ASHRAE Standard 55. So in summary, one of the main points we want practitioners in the industry to understand is that putting mass and energy into a space through heat and moisture is an HVAC system process. But creating spaces for people to sense and perceive thermal comfort goes beyond just the HVAC system. We have to look at all of the elements, and we have to appreciate that the thermostat set point and the requirements in building codes are not a proxy for thermal comfort, as we've already introduced here in today's module. So I want to thank everybody for listening. Thank to my other colleagues that will be presenting materials. And if you have any other further questions, you can go to the ASHRAE website through the Indoor Environmental Quality section, and there's an entire page of resources there on the subject. Thank you very much.
Thank you, Robert. Hello, everyone. My name is Deborah Steimel-Clair, and I'll be talking to you today about lighting design and how it relates with indoor environmental quality. Now, I believe that lighting design is a very important part of the built environment. In our society, we spend a lot of time indoors and under artificial lighting. This means we're exposed to it for most of our waking day. And that artificial lighting can really affect us both physically and mentally, the time that we spend under it. Good lighting design is an absolute enhancement of the built environment, along with providing the levels of public health and safety that we expect. But let's talk about it in terms of indoor environmental quality. There are 3 elements from lighting that interfaces with this. The first one is the quantity of light. The second is personal comfort underneath that lighting design. And then the quality of light. All of these things can affect our physical relationship to a built space. And then there are some elements of quality lighting that also are an enhancement of our built environment that I'm going to talk about today as well. But first, how do these elements of lighting design interface with the codes and standards that we reference when we do lighting design? And let's break it down. First, we have to really make sure everyone understands the differences between codes, standards, and voluntary rating systems. Codes are the legally adopted documents by the local authority having jurisdiction, the AHJ, for different cities and regions. They select the documents that set the bare minimum requirements for human safety and performance of buildings. When it comes to lighting and electrical systems, that also means preventing fires. Industry standards is when we bump up and talk about standard of care in the industry. This often goes above and beyond code, setting the reasonable expectations for buildings. These are often set by specific industry groups, ASHRAE being one of them. But when it comes to lighting design, we're talking about the Illuminating Engineering Society of North America, often talked about as IES. They set the lighting standards that we refer to. And then the last group is rating systems. This is a voluntary method that people can choose to evaluate their buildings and designs on in terms of certain focuses. Okay, we can evaluate the construction, the design, the performance with a look in terms of energy or wellness or various things. If you've ever heard of LEED, Energy Star, WELL, Green Globes, those are the voluntary rating systems that I'm talking about. When it comes to lighting design and codes, we interface with them in regards to required lighting controls, the maximum allowed energy used for lighting design. We also interface with ADA requirements in terms of where can we put control switches, making sure that they're accessible to all people. We do also interface with electrical codes and building codes when it comes to the materials for light fixtures and their UL listings, and the bare minimum requirements for emergency and egress lighting and exit signage. But when we want to get into design specifics, we need to move up into the industry standards, the standards of care. IES writes many, many documents that describe design criteria, design recommendations, and target illuminances for a variety of buildings in the built environment. And the best one to reference for indoor environmental quality would be the IES Lighting Practice LP1-24. which is a focus on designing quality lighting for people and buildings. There are other lighting practices and documents that they write, but that's probably the best one that I would recommend in terms of our discussion today. Lighting designers also interface with other standards, such as NFPA 101, 130 for life safety requirements, and specific illuminances for specific tasks. And then, of course, there's the voluntary rating systems. Voluntary rating systems, you get to earn points by doing various things in your building design. And when it comes to lighting, we have some that are based on physical components and some that are based on design. So physical component points would be looking at the materials of our light fixtures, the chemicals used, how recyclable are they, and what is their energy efficiency. The design points focus more on comfort and quality. We talk about accessible additional controls for flexibility, having quality color and light fixtures that reduce glare in spaces for light quality, having lighting designs that support circadian rhythms, having access to daylight and views, as well as exterior fixtures that are night sky friendly. So to sum up, the IEQ elements of lighting design really aren't addressed by code. The best thing to do is to go to industry standards to find that technical guidance. And while rating systems might induce you to go after certain elements, they're still going to point you back to those industry standards for technical guidance because they're just a guideline element. So going back to the core elements of indoor environmental quality and lighting design, how do we address these? Well, let's break it down. When we talk about quantity, we're talking about illumination levels. Are we hitting the Goldilocks zone, or are we too bright, or are we too dim? This directly relates to human comfort in a space. Then we talk about personal comfort under that light, reducing or removing eye strain that is caused by our lighting systems. There are many elements that can impact this, and this is what we call visual comfort in the lighting world. And then, of course, there's the quality of the lighting design, being able to include daylight, view access, and circadian rhythm lighting to improve the quality of the built environment. So let's talk about illumination. This is what people think of most when it comes to lighting design is, can we see what we're trying to do? We want to hit that sweet spot, that Goldilocks zone. We don't want to be overlit or underlit. When we're overlit, we're too bright. This is called overstimulation and causes muscle fatigue by working the eye muscles too much. It can worsen medical conditions, and if you have very high levels combined with long exposures, it can actually damage the eye. If you've ever heard of snow blindness or welder's flash, this is what we're talking about. The opposite is also true. If we're too dim or we are understimulated for our task at hand, we have similar results. Our muscles fatigue by trying to take in light that doesn't exist, and it can exacerbate health issues. And the way we can address this is by using proper illumination levels for each space and task, and really think about the use of the space when we set those target illumination levels. The next thing I want to talk about is personal comfort under lighting. So we're trying to reduce and remove eye strain. It is the most common problem related to light. Unchecked, it leads to headaches, tension, nausea, and stress, and is brought about by 4 factors. Improper illumination, which we just talked about, flickering within our light systems, glare, and contrast. So we have to remember that the eye is just like any other part of the human body. It relies on muscles to do its job. It allows us to focus on near and far objects, be able to see under all different kinds of light conditions with those muscles. And like any kind of muscle, they can experience stress and fatigue. This is what we call eye strain. Eye strain is actually increasing right now with the use of screens in our world. So it is actually recommended now that people take a break from screen use. Give your eyes a break. And the best way to remember to do this is the 20-20-20 rule. Every 20 minutes, you take a break for 20 seconds and give yourself the chance to look at something that is 20 feet away or more. Now, I don't know about your working space, but my office isn't that big. So I actually have to physically get up look out the window behind me, or maybe go for a walk down the hall to give myself this break. And it really does help with how I feel and how comfortable I am in a space throughout the day. Flicker. Flicker is something that happens in our lighting systems that not everybody notices, but people feel. The thing is our power systems is an AC sinusoidal wave. It goes up and down and up and down, and there's high points and there's low points, which means that our lighting systems actually have slightly higher levels and slightly lower levels as the power goes through this sinusoidal wave. Some people can observe this, some people can't, but when you pair LEDs with incompatible digital controls, all of a sudden everybody sees it, and it's really annoying. Flicker can really exasperate medical conditions for people who experience chronic migraines, and it increases issues for people with photophobia as well. When it's really bad, flickering can also induce the stroboscopic effect. That is when moving objects actually appear still because they're syncing up with that sinusoidal wave of the lights. As you see in this picture on the slide, this moving ruler that's being shook back and forth looks like caught still images because of this stroboscopic effect. Lighting designers can reduce flickering through careful selection of quality fixtures and intentional coordinated pairing of digital controls with those fixtures where everything works together well. All right, glare. Glare is another big part of comfort within a built environment when it comes to lighting design. There are different types of glare. What we most commonly think of is distressing glare. We've all experienced it when we've driven down a highway at night and a car comes at us with their brights on, and all of a sudden we can't see because their lights are too bright and directly pointed at our eyes. That is disabling, distressing glare. But we can also get direct glare from light fixtures. If something is overhead but in our field of vision and just a little too bright, we kind of want to block it out so that we can see the task at hand. This is direct glare. There are some more subtle forms of glare as well. Veiling glare is when you might have a shiny piece of paper, like a magazine, where all you can see is the reflection of the light and not the words on the page. That's veiling glare. It's a little more subtle, but still something we try to avoid. And we also get glare on surfaces. We've all had moments where we've had to tilt our phone or our iPad to be able to see the screen underneath because we're seeing light reflected off of that glass surface. That's glare from surfaces too. Designers can proactively work to reduce glare in their space by selecting fixtures that eliminate direct glare and reduce other types of glare in their design. The last thing I want to mention is contrast. Contrast really does affect visibility and comfort within spaces. As you can see with sort of the tongue-in-cheek graphic on the screen, contrast does affect visibility, not just with the task at hand. Can I read the black letters on the white paper? But if my desk surface is super bright and my walls are super dark because I have high levels of contrast in my workspace, that's going to make me feel uncomfortable, and it's going to increase eye strain. We also have to think not only about contrast of illuminated surfaces in our different spaces, but contrast between spaces. This is called adjacent contrast, when we have to move from a very bright space to a very dark space or vice versa. It takes time for our eyes to adapt to the different light levels, and there are moments when I can't quite tell what's going on because I'm still adapting. We've all experienced this if we've ever traveled through a tunnel going from super bright to super dark or vice versa. We all know it takes time to be able to see what's going on. We wrap all of these elements under what we call visual comfort in the lighting industry. Now I want to talk just briefly about quality elements in our lighting designs as well too. These are quality elements that are called out specifically by voluntary rating systems for indoor environmental quality. The first one is daylight. Providing access to daylight gives us a dynamic lighting source in spaces that people are attracted to. People feel like having daylight in spaces increases the quality of the space, increases the aesthetics of the space. And we actually have historical data that proves it increases our health and well-being when we have access to daylight too. It promotes our circadian health and gives us an opportunity for energy reduction when paired with daylight harvesting controls. But we have to be careful with daylight, because by adding daylight, we are increasing our solar heat gain, and if not designed appropriately, can increase contrast and glare within our spaces too. So it must be designed with intent and purpose. Another thing that provides increased quality is providing access to views. This gives us our connection to the outer world when we're indoors. It lets us know what's going on with our environment, the weather, the time of day. It increases that biophilic connection and the biophilic design of our built environment. Again, people perceive this as providing increased quality and higher aesthetics in our built environment, and we have historical data that it increases our health and wellness. But it all depends on what the view is that we can see out our window. If it's a beautiful landscape space with trees and grass, we are good to go. But if all we're seeing is just a red brick wall a couple feet away, it doesn't have quite the same draw and benefits. And the last thing I want to talk about when it comes to quality of lighting is circadian lighting. We have to know that light is a drug. Our exposure to light actually affects our endocrine system and the chemicals that flow throughout our body. This is called our biological circadian rhythms, and it sets us to the time of day following the sun so that our body knows, hey, it's morning, it's time to wake up. It's time to eat, it's time to use the restroom, now it's time to sleep. That is all tied to our exposure to light. So lighting designers can help keep that entrainment going in our bodies by increasing our access to natural daylighting or by mimicking that natural light pattern to positively affect our physical health. When we do that, we use blue-enriched light during the mornings and early afternoon, and then we remove that blue-enriched light at night because it's those specific wavelengths that trigger that biological chemical reaction in our bodies. So to sum up, lighting design can be a large part of indoor environmental quality, from the quantity of light to personal and visual comfort under that light, as well as impacting our health and wellness through daylighting and circadian health. Industry standards and guidelines are going to be the best resources for lighting designers to do this, as our codes are bare minimum requirements and do not address indoor environmental quality. Thank you so much for your time, and now I'm going to hand it off to Erik.
Thanks, Deborah. We really appreciate your input. Hi, my name is Erik Miller-Klein, and I'm going to be talking about indoor environmental quality as it relates to acoustics, the impacts on people, codes, and other design considerations. When we're thinking about acoustics, it's really important to understand that there is research that's found that sound is directly impacting people's health. Excessive noise can increase your blood pressure, reduce your cardio output, and it can also increase your fatigue. There's also studies on sleep that have found that different types of sounds at different loudnesses can disrupt sleep and can make it so that you're not as restful. And so again, you're having long-term health impacts. Now, in that same context, though, there hasn't been a lot of work or specific research that's done as good of a job on evaluating causality. We have a lot of strong associations. So there's opportunities for us to better understand how different acoustical principles are impacting people's health. And that directly relates back to how that's going to impact the spaces that we design for people, both the places that they live and work. Now, when we think about the places that people live and work, it's really important to think about the information that we do get feedback on. And right now, that's primarily on the places that people are currently working in commercial occupancies. The Center for the Built Environment at the University of California, Berkeley has done 20 years of anonymous surveys of commercial occupants. And what they have ended up finding is that 39% of the respondents said that the acoustical quality of their work environment was negatively impacting their ability to do their job. That's a huge number to think about. Like, how are we going to better understand and deliver the types of buildings that we want if we're still like getting a D as an overall industry? Now, even in that context, they found that green buildings were getting worse scores than standard buildings. So really that's telling us that even some of our goals and our standards and design guidelines are not always delivering the quality of acoustic performance that we want. Now, there's also a missing piece to this information that we've got from CBE, which is that we don't actually have the buildings and metrics associated with the performances that are driving these opinions from the users. So there's still an opportunity for us to further understand how these buildings are delivering to these people so that we can provide better buildings. But one industry that has done a lot of work to try to understand this connection has been the healthcare industry. They have what are called the HCAHPS scores, which is from the Center of Medicare and Medicaid, which is actually part of how they reimburse hospitals. They're actually grading all the hospitals based on their quality of care. And that some of those are healthcare related qualities of care, but also there's a survey that's sent to patients 2 weeks after they've left the hospital. And the questions range from the cleanliness of the room, the quality of the staff, but also how quiet was it outside your room at night. And that quiet score is the most commonly underrated number on this chart. And now why that's important is that we know that we need to be better with acoustics. We know that people are evaluating quiet as what are they hearing, what are they experiencing. Now I think also the framing of night does mean that if people don't sleep well, they may also think that maybe sound was part of the reason they didn't sleep well. Maybe that's not always the case. But in that context, what they've actually found when Press Ganey did a detailed analysis of thousands of surveys was that as you can improve your quiet at night score, all the other scores, like the cleanliness and like the responsiveness of the staff, also improve by 0.75 points. So 1 point also improves the other questions by 0.75 points. So we know that the quality of the environments that people are experiencing is directly related to acoustics, which makes sense, right? You can imagine if I took you for a test drive and you were in the car with me, but you were blindfolded, and before I took off the blindfold and I asked you how much was the car that we just drove around in, you'd probably be pretty close. You could guess based on the quality that you experienced on that little test drive. So we understand, viscerally, like what are these spaces that we're in, and then we're judging them based on that different aspect of performance. So how does that relate to where we're at as an industry? Well, it's pretty interesting in that we have very few, codes and standards. Right now there are limited building codes right now in the United States as it relates to acoustics. And then on top of that, less than 10% of buildings are using acoustical design professionals. And then of those, less than 10% are doing any kind of commissioning to understand and qualify the performance of their facility at the end. And so we know what less than 1% of buildings are doing for the building occupants. And so we are actually working from a place of a lack of information. We don't always understand what it is that people are experiencing. So when we do see those surveys like the CBE, it's hard for us to understand like what's leading to some of those experiences. I mean, you can see from this table, K-12 education, there is a code within IBC. Some states and jurisdictions have their own requirements, and those may touch on only background sound. Or in this case, IBC talks about both background sound and reverberation time within classrooms. But you can see higher education, commercial construction, there's no codes. Those are all dependent on those institutions or organizations to make the decisions for acoustical design. And it's not to say that there aren't guidelines that they can reference, but again, those design teams have to understand or reference those to then apply that and then engage in that thoughtful design. But when you get into healthcare, we have things like FGI, which is adopted in most states and is a very clear design guideline. And then you also have in multifamily, at least with respect to airborne sound and footfall noise, a requirement for the design of apartments and condominiums. But there are things like ASHRAE's International Green Construction Codes that they support through 189.1 that is driving us to design and better understand acoustics in the built environment. Now, that also leads us to why are we in this state as the design industry? Well, part of it is that we've defunded detailed research into acoustical design for the last nearly 50 years, where in that same period of time, billions of dollars of money has been spent at the Department of Energy to investigate energy modeling and help drive some of the energy codes and building envelope decisions that we've been making. without consistent research, it's hard to sort of enhance and improve these different codes so that we can make sure that we're getting, better buildings and right sizing those. Whereas if you look at ASHRAE 90.1 and other local ordinances that are driving these energy codes, there's a lot of substantial research both at a federal level and within this organization to drive better design. And that is also needs to be kind of framed with the fact that buildings are prototypes. And when we are not testing those prototypes, we're not really understanding what we're delivering. Can you imagine if you were buying an appliance and it wasn't tested, and you were buying a prototype and you were testing it out and seeing if it's working? And then not only that, did you know who built it? And so I think kind of referencing and understanding that in the built environment, oftentimes we are disconnected from the design team, at least the users are. They're disconnected from the design team and the contractors, and they don't have a good feedback loop. Whereas a lot of the other things that we are regularly interacting with in our lives through consumer electronics or appliances or automobiles are things that not only do we know who makes it and the model, but we have a clear communication path and a way to probably even deal with like warranty or service calls. So how do we sort of think about that in the context of acoustics? Now, part of this is also in the context of how we think about acoustics is the fact that everything is a single metric. At least most commonly in these different standards. And you could almost think of single metrics as being taking these 4 famous pieces of art and boiling it down to the average color. And the average color in this case is brown. And it's like, and you can think about probably almost any color painting or piece of art that you can think of, probably at a foundational level, the dominant color or the average color is brown. And that's not really telling us the full picture. We don't know which paintings these are, right? Can you guess which of these is the most expensive? You might look at it and be like, oh, maybe it's this one, maybe it's that one. Well, I'm going to give you a little bit more information. And this is actually how acoustical designers would be considering the different metrics. We will look at things like octave bands or 1/3 octave bands, which is very similar to this idea of the 5 most dominant colors. So now that you're looking at the 5 most dominant colors, is it really that much easier to guess which of these is the most expensive? And probably it's still not that easy, right? It's not obvious. So, but understanding that now that you're seeing the full picture, you're seeing the whole painting, that's very similar to what the final users are going to experience with the acoustical performance of their facility. They're going to hear the full picture. They're going to see all the strokes. They're going to see the textures and the shading. And so we need to acknowledge that when we're thinking about how people are going to experience our spaces, they're going to be dealing with things like this in terms of the acoustics of a space is not a single variable. It is a multivariable problem. When we talk about things like sound isolation, it's really the perception of speech, and it's what we call speech privacy. So it's background sound as it relates to sound transmission. Or we even think about how loud an amenity space might be, or a large open office space, and that's a combination of mechanical systems, the building occupants, as well as reflected sound off of the different materials in that space, or even just background sound itself. Like it is a combination of building systems, maybe occupant noise, transmission of sound from outside the building, and how you hear that actually can be sort of filtered, but in terms of how it's measured and perceived can be very different from person to person. And so again, better understanding all these things. And we know there's these interactions and overlap with these IEQ parameters, and that's part of why we've got ASHRAE Guideline 10. So we know that there's ways for us to better understand these buildings. It's now aligning that better with the user's experiences and understanding. So what can we do next? Well, really we need to leverage our efforts to do better research, to understand what it is that is actually happening and how it's relating to people's experiences. We need to prototype. We need to test things. We need to break things. We need to think about and leverage the work that we see in other industries like consumer electronics and appliances, and like try to understand smaller components of the buildings that we're going to deliver so that we can better right size the solutions. And that also can help us be more efficient with both materials as well as cost. And we need to communicate. We need to understand how things are working, and then help the whole design team and the stakeholders understand how these things are going to relate to their experience in these spaces. We need to test. We need to understand commissioning, and understanding the final performance is critical, and also understanding and layering that with people's experiences. We are at a place where we need to be understanding everything we do. So many other industries are dealing with lots of data, or what we might reference as big data, but right now we aren't even understanding what 1% of our buildings are actually doing. So we can do better. We're now at a place where we can leverage all that. We can prototype, test, validate, we can optimize. All these parameters are meant to complement each other and deliver better buildings for our occupants. So then we need to put in those efforts. We have an opportunity to right-size design and construction so that it meets the needs of our building occupants. Energy efficiency of materials, embedded carbon, not just operational efficiency. Thinking about construction reviews, understanding the quality of the spaces and the details that are being completed so that we know that and collect data, understand how people are experiencing those spaces, and having that correlation between a user's experience and the metrics that we've measured in these spaces. We can all do better as long as we can work together to design better buildings. I'd like to thank all my other fellow presenters as part of this IEQ seminar. Thank you for attending.